Okay, well, thank you very much to the organizers for having me over. Thank you very much for everybody to stay here for an extra 20 minutes to listen to me. Yeah, this is the title of the talk. This is my motivation. There's an old philosophical motivation behind all of this work. That is, I've always felt a little bit sad for those poor tensor modes in all these models of inflation that were presented, that were detailing a lot of great phenomenology you can have with the scalars, and then there was always this sad paragraph at the end of the paper saying, and by the way, the energy scale of inflation is, so the amplitude of the tensor mode is. And that's it. So, in other words, we always had a lot of fun studying the scalar perturbations, and tensors were typically assumed to be kind of boring, at least for a theorist. No, we have amplitude of tensor that of course is very important because it measures the energy density of inflation, but other than that we don't expect a lot of. By the way, it turns out that there are a lot of experiments that are going after tensors, both at the CMB scales and at smaller scales, as you know, apparently gravitational waves have been detected now. So this is the motivation for the work. Now, the question is how to get those less boring tensors. And there's a number of ways, and one that I consider particularly appealing is the idea that there are excited modes of some other degree of freedom during inflation, and those modes can be excited because the inflating background provides a time-dependent background that is a natural setup for producing particles, and these guys can be additional sources of gravitational waves which can inherit the properties of the excited degrees of those excited degrees of freedom. So for instance, the prototypical example, and here when I first wrote this slide, I had a list of people that should have been mentioned for this, and then I stopped because it was going all the way down to the slide, was to consider the possibility that there is a secondary scalar, chi, who is totally irrelevant for basically all of the infinite inflation because it's coupled to the inflaton via this coupling, phi minus phi naught, that generates a large mass for the field chi, apart from the short amount of time where phi is close to phi naught. And then when phi crosses phi naught, chi is cheap to produce. We produce a lot of quantum of chi, and this quantum of chi can act as a source of gravitational waves, for instance. After that, phi keeps rolling, and chi becomes heavy again, and you forget about it. We studied this in 2011 with Jessica Cook, who was a student back then at UMass, and we discovered that yes, gravitational waves are of course produced, but they're also very small since the correction to the amplitude of the gravitational wave spectrum is given by the product of 1, 2, 3, 4 numbers, each of which is much smaller than 1. So the final result is really small. And the interpretation was that no relativistic degrees of freedom, particular scalars, are a poor source of gravitational waves that like to have quadrupole moment. And if I have time, I will go back to this point towards the final part of the talk. So we tried something different. And Ricardo Ferreira mentioned this model. I will try to be so consistent and refer to it also here. So we considered an inflaton that is a pseudoscalar with a broken shift symmetry. Let's think about natural inflation. This is extremely well motivated by theoretical naturalness conditions, and I would give another 1 hour talk on this if I could. And it is naturally interacting with some abelian H field. This coupling is absolutely natural, is actually in a sense unavoidable. Of course, what is important is the magnitude of this parameter f, the coupling constant. If it is 10 Planck masses, then forget about it. So what happens? Well, we saw this equation before. The main property is that the two helicity modes of the photon, lambda equal to plus, lambda equal to minus, have a different equation of motion, and they see this different master that in the case of the negative helicity mode, if phi naught is positive, or positive helicity mode, if phi naught is negative, appears as a tachyonic master. As a consequence, one can solve actually this equation exactly. One discovers that there is an exponential amplification of only one mode of the photon. Let's say the left-handed one depends again on the sign of phi dot, or phi dot over f. So we see that during inflation there's an exponential amplification of only left-handed, let's say, mode of this gauge field. One can compute the amplitude is given by this quantity. Notice that the system is parity violating in the first place, and as a consequence you have left-handed photons only as a signal of parity violation. And then the energy in these magnetic waves is a source of gravitational waves. One can write the equation for motion for gravitational waves, blah, 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 and one discovers that the amplitude of left-handed gravitational waves has a two-point function that is different from that of the right-handed gravitational waves. And I will not spend time on the figure. One can sit down and compute things in this model, and one discovers that really the left-handed and the right-handed components have one standard part, that is the one in red, and in blue you have these two different coefficients, and these different coefficients signal the fact that there are different amplitude of gravitational waves and parity violation. One, for the students or younger people in the audience, this is a lesson on not putting 2 pi equal to 1. This 10 to minus 7, 10 to minus 9 are actual numbers. It's not parameters, it's results of 2 pi's and factorials and powers of 2. So the main result here is that we have left-handed and right-handed gravitational waves that are different, and that this component can actually dominate the vacuum component, which implies in particular that we might have no relation whatsoever anymore between the energy scale of inflation and the amplitude of gravitational waves. And one can hope to have detectable tensor modes even if inflation happens at very low scales. Not only, now we have a bath of photons that are sources of gravitational waves and in general metric perturbations in a 2-to-1 process. This means that everything that is sourced is non-Gaussian. And so one nice side effect of this is that the gravitons get a large non-Gaussianity. And by large I mean that the 3-point function is proportional up to a coefficient of order 1 to the power 3 over 2 of the 2-point function of the graviton, which is also kind of cool. Unfortunately, in the same way as tensors are produced, scalars are produced, and we have very strong constraints on the amplitude of scalars. So if one follows this very simple model that I presented of just a uniformly, slowly rolling inflaton coupled to photons, it turns out that there are strong constraints on the value of this parameter psi, phi dot over fh, that implies that all the signatures I mentioned above are not visible. Because once I impose the constraints on FNL, everything becomes very small. There's ways out, and I assume Marco Peloso will talk more in detail about this. If the field that is coupled to vectors is not the inflaton, and if it rolls only for a few e-folds, that is not a totally crazy assumption, then all the phenomenology I mentioned before, parity violating gravitational waves, non-Gaussian gravitational waves, still holds. In particular, at the level of observations, this means potentially an EB and TB correlators, not clear whether this will ever be observable, potentially 3-point functions of T modes and B modes that are also non-vanishing, also in the parity forbidden configurations. For instance, BBB with L1 plus L2 plus L3 equal to even. And all the other non-boring properties you want to expect from your tensors. You could have bumps in the spectrum of B modes. In particular, possibly blue B spectra. Which brings me to the next. I still have time. Perfect. The next part, that is, since the spectra are blue, and this was partially mentioned also this morning by Rob Caldwell, since these tensors are blue, we expect to have a lot of them at small scales. And at small scales, we have interferometers. So as I said, this is the amplitude of left-handed and right-handed gravitons, and as I said, psi, this parameter psi that appears here in an exponent is proportional to phi dot over h. During inflation, phi dot increases and h decreases. So at later times, that is smaller scales, this stuff can be large. And in principle, might be detected by interferometers. And by the way, at those scales, of course, we don't worry about non-Gaussianities because nobody has measured FNL at a scale of 3,000 kilometers. And for instance, this is an example of a curve. This is many others' paper on possible detectability by LISA of these effects. The blue curve is the prediction by the model. Here you can see actually there are three sections in the curve. This part here is the standard part where the additional photons are still small enough that they don't contribute to the tensors, and this is just the usual vacuum fluctuation tensor modes amplitude from chaotic inflation in this model. Then you have this exponential increase that I was mentioned before, e to the 4 pi psi, with psi that goes as some square root of number of e-folds. And then in this region, actually back reaction kicks in. Photons become, the photon population becomes large enough that it back reacts on the inflating background. And one can account for it in some somehow trustable way. And we expect in any case a plateau. And as you see, I mean, choice of parameters is not totally ridiculous. This is chaotic inflation with f equal to m Planck divided by 35. And it goes exactly through the sensitivity curves of LISA. Back to the explosive production of scalars, I'm going to re-show a couple of slides I showed at the beginning of the talk, just to refresh your memory, because it's late. As I said, the original model was considering an interaction of this form, and the interpretation was that and this was leading to a production of chi particles here that was leading to the production of gravitational waves, and this was very inefficient. The source gravitational waves divided by the vacuum gravitational waves was a factor of 10 to minus 7 times this number. So small, small. So we asked the question, and the interpretation was always that non-relativistic modes are poor sources of gravitational waves. So we asked the question, this was with Cody Gould-Picot, still at Amherst. We asked the question whether we can think of producing those particles, chi particles, but then keep them massless. Does this improve things? And does it improve enough? So we consider a model that is kind of contrived, in which we have some sort of symmetry restoration. You have a third field sigma that acts as an order parameter for symmetry breaking. The inflaton is phi. When the inflaton, I can always shift the potential of the inflaton in such a way that when phi crosses 0, sigma goes from a non-zero expectation value to a 0 expectation value. And then I use sigma as mass for a third field chi. So I have this field chi that whose mass is given by sigma squared. Sigma squared is very large and then becomes 0, and it stays 0. And I produce a ton of these chi's, and the question is a ton of chi's enough to produce enough gravitational waves? And the answer is, well, first of all, this is some typical shape of the tensor spectrum, bumps that go down quite slowly. We have the parameterized amplitude at the peak that depends on the parameter of the theory. You don't really care about this. But actually, this is just to show that we did the calculation. The result is that things are slightly better, but once we impose many constraints, this is a contrived model, as I said, of which I have to impose many constraints, I have an improvement. Remember, this number was 10 to minus 7, now it's 10 to minus 4. There is some improvement, but not quite enough. So still forget about it to see the stuff in inflation. This is about 3 orders of magnitude more than the original case of massive chi, but still too small for a single chi species. Then we played the game on trying to see whether we could see it at LISA scales. Still, you have to push parameters crazily. In principle, let's say it's not illegal to see it seeable at Lisa scales, but you really need to make a lot of assumptions, like, potential becomes very steep near the time, and at the same time you have several species of this field, so, if I had to bet money, I wouldn't bet money. And since I have 2 minutes, I can even advertise work in progress with a lot of people, some of which are here, Peter Ratchet, Marco, Lauren Pierce, and one starting student at UMass, Mike Roberts. How about fermions? Usually fermions are considered really the kind of particles you don't want to care about during inflation. Mostly because of Pauli blocking. But also because, well, even if I don't have Pauli blocking, usually you can use, one can consider two limits. If the fermion is really light, fermions are conformally invariant, you don't produce them. If the fermion is really heavy, the fermion is heavy, you don't produce it. So the only possibility of having fermions that are produced usually during inflation is to assume that the mass m is of the order of the Hubble parameter, in which case everything is of the order of the Hubble parameter, and that's not enough. However, if we take our favorite models of inflation that have shifted symmetric inflatons, there's also this coupling to fermions. And it turns out that this fermion that I called Y for some reason has no value of occupation number up to large values, phi dot over f, that can be much larger than a Hubble parameter. So even if you have Pauli blocking that prevents you from creating large occupation numbers at small scales, you can have a large UV cutoff, so you still produce a lot of fermions. And the part that is work in progress is whether this lot of fermions, are they going to produce a lot of gravitational waves? And if yes, are they also going to produce a lot of FNL? In which case, we might have a problem, but we don't know. I can even conclude. Well, blah, 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 blah. The main thing is disentangle amplitude of tensor from energy scale of inflation. That's the main take-home message. Thank you.